Hello, this is Nasnianowski. We're doing monoidal category theory. We're going through every section of the book. We're up to chapter 3, structures within categories. Last time we did products and coproducts. Those were the simplest structures, one of the simplest structures. And now we're going to do limits and colimits, which are more general. Okay, types of structures that we'll see. Okay, so let's go back and see products again, okay? Because we saw products, let's go back. So what did we say? We said we give an object A and we give an object B. What's a coproduct? What's a product? It's another object. I'd like to do this a little more interesting. I'd like to think of this as a diagram. So we're going to put it in a box and we're going to think of it as a diagram. And then what we do is, what's a product? It's an object that somehow completes the diagram. In other words, it dominates, or it's on top of the diagram and it dominates it. Okay? Now, it doesn't just dominate it, it dominates it the best fitting domination, which means, I shouldn't use the word dominate. Let's use the word completes. It completes the diagram, which means if there's any other object here and there's any other map here, then there's a unique map like this such that everything commutes. Okay? So that's just another way of looking at a product. It's some diagram and you're completing the diagram. You're putting something on top of it. Okay? And doing it in the best possible way. Okay? Let's look at a coproduct. Coproduct is you have the same diagram, but now you're co-completing it. What does that mean? Well, from every object in your diagram, there's a map to it. And if there's anything else that co-completes it, so this completes the diagram, this co-completes the diagram, then there's a unique map like that. So we get a nice notion. Okay, and this is what we're going to do the entire class today. We're going to look at diagrams, okay, and we're going to complete them, and we're going to co-complete them. And we'll see what we get. Okay, good. Okay, before we start, let's look at another diagram. Okay, A1, A2, A3, A4. This is a diagram that has, instead of having 2 objects, it has 4 objects. Okay, just to make things a little bit more interesting. Okay, great. Now, what's the completion of this diagram? Well, it's the product with 4 elements. Okay, and this product completes, which means there's a map from it to every element. Okay, and it satisfies some type of universal property, namely, if you have any other object that completes it, then there's a unique map from C to that. Okay, so that's a bigger, more complicated diagram, and that's a completion of it. Okay, it's the best fitting diagram that completes this more complicated thing. Okay, great. We can also co-complete this big diagram. A1 plus A2 plus A3 plus A4. Okay, and there's maps like that. And if there's any other object, C or D, let's call it D, okay, that co-completes this diagram, then there's a unique map like this, which makes all these triangles commute. Okay? So again, it doesn't only work with 2 elements, it can work with n elements. In the book I also talk about what happens if the diagram's the empty diagram. Well, you get the initial object and the terminal object. What happens if you get just one object by itself? Then you get an identity morphism. Okay? So we go through that. Okay, great. Now, we did this for 4 objects. You can do it for any amount of objects. In fact, you have the following notation. if you have a set of objects, okay, and you have I member of S, so then you can take the product of all of them, AI. Okay, so that's a notation for the product of S object, the number of elements in S objects. Okay, you could also take the coproduct. Coproduct, part of duality, so we turn the product upside down. Okay, and it's to make you think also of disjoint union. So you have I member of S, and you have AI. Turn the product over. So this is the product of many elements. This is the coproduct of many elements, and we'll see how these map. Okay, great. Okay, great. Good. So those are simple diagrams with just a bunch of objects in them. But what about a more complicated diagram? In other words, diagrams don't just have objects, they can also have maps in between them. So let's say you're given a category and a map F from A to B. Okay, so that makes a nice diagram. We would like to complete this diagram. So what does it mean to complete this diagram? Is some object C, okay, and it has maps like this. Okay, but now we require that the maps commute. That means from here to here is equal to this. So we didn't have this commuting thing because we didn't have any arrows before. Our diagrams before were discrete. They were separated. Now we have maps in our diagrams. Okay, but we want this to satisfy a certain requirement. Namely, if you have another object D and you have another map like that, and like that, such that D, like this map composed with F, is equal to this map, then yes, that satisfies it, but this satisfies it the best, which means that there's a unique map like that, which makes all these diagrams commute, which makes all these triangles commute. Okay? So this is going to be a completion of this diagram. Okay, so this is what a limit is. Take some diagram of arrows and objects in a category and look at something that completes it. What's an object that completes it? And again, these are usually not a object. Is usually not the object. Is usually a object. There might be more than one, but they're unique up to a unique isomorphism. Okay. That's called a limit of this diagram, and again, we're going to have more and more complicated diagrams as we go on. Okay. We can also take the co-completion of this thing. Okay, what's the co-completion? It's a map like this to this, and a map like this to this, such that this commutes. And it's the best co-completion that you can possibly have, which means if there's any other object with such that this commutes with this, okay, then there's a unique morphism like that. Okay, so you have limits and co-limits of simple diagrams like this. Great. Now, I just made a legitimate definition. I would like to see an example of such a thing. Okay, and here's a nice example of it. Okay, so let's look in the category of sets. So you have S and T, and you have a nice function f from S to T. Okay, so I want to look at the limit of this function. Okay, and I'm going to show you what the limit is. It's a set with a map like this to this. Okay, and I'm going to just define what it is. And once you see it, you'll be able to see what it is. It's pairs of elements, S. Okay, but watch what we have. We're going to have pairs of elements. We're going to have another element here. And watch what we're going to have. This is going to be a projection function. I'm going to project down this. Okay, and this is going to be a projection. It's going to project down here. So you might say this is going to be an element T, but it's a special element of T. Okay, so this is going to be a projection. So we're going to project these pairs, and I didn't finish writing it up, onto the first element, and then we're going to imply that, and we want it to be the same element over here. So this is going to be f of s. Okay. Okay. This is going to be a member of S cross T. And that's it. Okay. So what is R? It's the subset of elements in here and here, such that you have this. Okay. This is called the graph of F. Okay. In regular set theory, this is called the graph of F. And you have a function, and this tells you how it is, what it looks like. So that's nice. Now you have to understand, there might be other sets that do this. Okay? But if they're going to satisfy this, if there's maps like this, and if they satisfy it, then this one basically is going to be smaller than this. So this will be, R prime will be some of the elements R. Some of the S comma Fs. So, but if you want all of them, you have to have the best fitting one, and that's all of them. Okay, that takes care of that. Okay. Okay, great. We can also take the co-completion of this in the category of sets. Okay. So let's do that again. So you have T and you have S, and we want the co-completion. So what that's going to be is another set V, and there's going to be a map from here to here, and there's going to be a map from here to there. Now beforehand we had projections. Basically here we're going to have inclusion maps. Okay, and let me tell you what V is going to be. V is going to equal to the disjoint union of S and T. The disjoint union of S and T. Okay, but one second. So S includes into the disjoint union, T includes into the disjoint union, but we want something that takes into account this, namely, you have a map from here to here. And so what this is take the disjoint union and then put an equivalence relation on the disjoint union. And the equivalence relation is basically it's generated by the following. F of little s, pick a little s over there, see what it's set up to, and make that equivalent to little t. No. Nope, sorry. No, sorry. F of s is equivalent to little s. So what you're doing is you're crunching the source and target. Basically, let's go through that. Little s here is going to go to that thing. Then if you apply this to it, you're going to get this. So f of s, so here you have little s, here you have f of s, okay? And you want these two things to be the same. So you want that s is going to be equivalent to, that's a quotient set of f of s. Okay? Okay, great. Okay, so we're looking at various diagrams, and we're completing and co-completing these various diagrams. We started off with the discrete diagrams, where there's just objects, and then we moved on to discrete, diagrams with one map. Let's look at more complicated diagrams. Okay, so let's look at this. You have an object A, you have an object B, and now you have two maps between them. Okay, and you have F and G between them. Okay, so this makes a nice diagram, and I'd like to complete this diagram. Okay, so what's this completion of the diagram? Well, it's going to be some object C such that, and a map from C to B, from C to A and C to B, such that, now what do we want to commute? We want this to commute with both of them. This, I don't know, we'll call it PA, PB. So what we want is PA followed by F should also equal to PB. But we also wanted to complete the G also, so PA followed by G should equal to PB. Okay? And we want it to be universal, namely, if there's any other map that satisfies such that both of these diagrams commute with the F and the G, then that's very good, but you want it to be like that. Okay? It's the best fitting object and maps that satisfy both of these requirements. Okay? This has a name called an equalizer. Okay? This is called an equalizer. It's usually written a little bit differently, but this is explanation very nice. This is a very clear explanation of what you want, and it's exactly true. But the way the diagram is usually written is like this. You have an object C, and the C maps into A, and you assume, so we'll call this P of A. I'm sorry, I want to call this E for equalizer. This map is an equalizer, which means E followed by F is equal to E followed by G. Okay? And it's the best fitting one. We'll talk about what that means in a second. But the reason why this notation is no good is because you don't really see the way we did it before. We saw that it has to commute. But here we don't see it, but we say it. This followed by this is equal to this followed by this. Okay? Okay, what does it mean, the best fitting? That means if you have another object D and you have another map like that, such that, let's call this E prime, such that E prime followed by F is equal to E prime followed by G, then there's a unique map like that, such that this triangle commutes. Okay? So again, this leaves out the fact, but you have to state it, that these two diagrams have to commute. Okay, great. That's called an equalizer. Hold on. Let's erase this. Erase all of this. Okay. And by duality, there's another thing, and we want, let's call that C. Okay. And we want something called a coequalizer. What's a coequalizer? Coequalizer. Okay, well, it's a map like this and a map like this, such that F composed with this is equal to this. G composed with this is equal to this. And it's the best fitting one. What does that mean? That if there's any other object like this, then there's a unique map like this. Okay, so that's a coequalizer. This guy with this map is a coequalizer. Again, it's not usually written like this. It's written another way, but we have to then state what we mean by that. So it's usually written like this. Here's your B. Well, a coequalizer. So I don't know. I'm missing a letter. Let's call it E again. Okay, and what this is basically F composed E is equal to G composed E. Okay? Okay, great. Oh, what does it mean to be universal? Well, it means if there's any other map, let's call it E prime, such that F composed E prime is equal to G composed E prime, then there's a unique map like that, making this triangle commute. Okay, so we're seeing this universal properties over and over and over. Okay, we want something that fits, and we want it to be the best fitting. We want to complete the diagram, and we want the best completing of the diagram. We want to co-complete the diagram, and we want the best co-completion of the diagram. Okay, great. Now, let's look at what this means in terms of sets. And again, what we have to do is, just like we did in products, in coproducts, we have to look in a lot of different categories and see what they are. We're just going to look in sets over here, and every time we need it, we're going to say what it's equal to. Okay, but sets is obviously the way we learn these topics. Okay, so let's do this. You have a set S, you have a set T, you have a function F, you have a function G. Okay, and now we ask the following. what is the coequalizer? I'm sorry, what is the equalizer? So we'll call it E, like that. Okay, what's the equalizer? And I'll tell you what the equalizer is. It's going to be a subset of these guys, so this will be an inclusion. It's going to be a subset, and so we write it as follows. We write it as follows. E is equal to the set of S, member of S. It's going to be these guys such that f of S is equal to g of S. Okay? It's those guys in here that this maps to the same thing as this maps. Okay? Now, that's an inclusion map. Okay? And look what it says. If you pick a guy where f and g are equal, include it into here, do f. Well, that's the same thing as picking a guy where f and g is equal, include it into here, do g. It's the same map. Okay, so this map from here to here is the same thing. Okay. Now, again, you could have an E prime, but basically E prime will be subsets of this. You want the largest subset. You want all the S's such that f of S is equal to g of S. Okay, very nice. That's the equalizer in sets. Okay, what's the coequalizer in sets? So we'll call it C for coequalizer. We'll call this for projection. Okay, making up the names as we go along. Okay, and basically what's this? Well, C is equal to take T and take the quotient set of that. So we're gonna set certain things equal to each other. What are we gonna set? Well, we're gonna set, to make sure that this works, we're gonna set, right, we're gonna take, it's gonna be, this equivalence relation is gonna be generated by the following things. We're gonna met f of S is going to equal to g of S. Okay, so that's not always true, but in other words, f of S is not usually equal to it, but what we do is we crunch the elements and say, look, whatever this goes to, set that to be equal to, that's going to be the same as this. Okay, now look what we do. Pick a typical element here, followed by f. Okay, so this is going to be f of S. Happens to be also going to be, okay, that's going to be f of S. There's going to be another element, g of S. We're going to crunch those together to be 1 in this quotient set. And so this map followed by this map, this map followed by this map is equal to this map followed by this map. And so you get a coequalizer. Okay, so that's the way it works in sets. Great. Okay, let's look at a more complicated diagram. Okay, back up. We did discrete diagrams. We did a map with, we did a diagram with one map. We did a diagram with two maps. Now we're going to do a diagram with two maps, but a different form of the maps. And the diagram is going to be as follows. Let's say you have an object A, and you have an object B. You know what, I'm sorry, I think I should do this as a C. This is a C. And you have another object B. Okay? And now you have two maps, but the two maps are not coming and going from the same place as we did with equalizers and coequalizers. The two maps are like this. We'll call this F, we'll call this G. Okay? And now what I'd like to do is, I'd like to complete this whole diagram. Find me a thing that completes it. What do I mean by a thing that completes it? Okay, and so we're going to call this A cross B, okay, with a little C in it, but it also has to take into account F and G. Okay, in fact, you could just write F and G because the codomain of F and G is the same, so F and G. Okay, so you have to take into account when we're completing it, it's not just completing the objects, you're completing the map. Okay, great. What is this? Well, there's going to be a map from here to here. There's going to be a map from here to here. Okay, now I'm going to draw another map, which is never drawn, but it's very important. What does it mean to be a cone-completion of a diagram? There's a map from it to every object in the diagram, such that everything commutes. What does that mean? Well, it means that this commutes with this followed by this commutes with this followed by this commutes with this. Now, since they're both equal to this, we can forget about this, and we can restate it as follows. It's an object in the category with maps like this to this. By the way, this is usually called pi of b, and this is called pi of a. Okay, it's a map such that pi of a followed by g is equal to the middle one, which is equal to pi of b followed by f. So it's those things that satisfy both. Okay, but they're universal. What do I mean by universal? If you have another guy, D, another object D, and you have a map like this, and you have a map like this, and you have a map to the middle, but we don't have to write the map to the middle. Main point, this followed by F is equal to this followed by G. That also satisfies the requirement. Then, dot, 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 dot. There's a unique map from here to here such that this commutes, this triangle commutes, and everything commutes. Okay, so that's what I mean by completing. This is a completing of this diagram. It universally completes it. It has to be the best fitting thing. We call this a pullback, or a pullback square. Pullback. Okay. Okay. We usually don't look at a co-completion of this diagram. Okay, now let's switch. Let's look at duality theory. We don't look at a co-completion of this diagram. What we look at is this diagram. Okay, and we write the co-completion as follows: A disjoint union, or not disjoint, coproduct B, okay, also has to take into account F and G, okay, and we have maps like this to this, such that this commutes with this. We'll call it ink. We'll call this ink. This followed by the inclusion is equal to this followed by the inclusion, and it's universal, which means if there's any other object like this, then there's a unique map like that. Okay, that's called the pushout. Okay, great. So this is a definition within any category. Let's look at sets and see what this is equal to. Okay, hold on. Okay, so we want to look at what a pullback is for these sets. So you have T, U, S, you have like that. Okay, and the answer is as follows. It's, we write it as follows: S cross T subset FG. Okay, and let me just tell you what it is. It is equal to those little s, comma, little t's, here and here, member of S cross T, such that, okay, such that F of S is equal to G of T. In other words, it's equal to pairs of elements from here to here that land in the same place. So again, lots of different things can go on to different places, but if they both land in the same place, then they're part of this subset. Okay, this has a special name. It's called a fiber product. Fiber product. Okay, in sets. It's used in topology, it's used in physics. Fiber product. Okay. Okay. Now, there's a special case of this that's very important. Namely, what happens if this is an inclusion function? Okay, in the book I do it the other way, but it doesn't matter, it's the same thing. Okay, then what this is called is f minus 1, because really what we're dealing with is this f function. This is an inclusion of t. Another way of saying that is, this is those objects in S. I'm sorry, this is those objects in T such that, I'm sorry, this is those objects in S such that it's the pullback of that. You know what? I'm going to get in trouble here. So let's follow exactly the book. The book has it right, and we'll do it exactly like the book has it. Okay, so what do we have? The graph, the equalizer. Okay, it's called the pre-image. So it goes as follows. You have S going to T, regular function, and you have R, a subset of T. Okay, and that's in G, but it's really an inclusion. Okay, and here's F, and this is what's called F minus 1 of R, which is equal to those S member of S such that F of S is a member of R. Okay? Okay, so you have this function here, and this goes like this, and this goes like this. This is an inclusion. So it's those S, see, it's a subset of S, those S, such that when you take that, it lands in here. Nice way of seeing it in terms of Venn diagrams, okay? Namely, you have T, you have a subset R, okay? You have S, you have a map from here to here, called F, okay? And what's this guy? This is F minus 1 of R. This is those things that land in here. Okay? And it has a special name called, not a fiber product, but a pre-image. Pre-image. We're going to use this a lot when we talk about power sets. Okay, so it's the pre-image of F of R. Okay, great. Okay. Okay, now dual to pullbacks, we write pullbacks like this, but dual to pullbacks is something called a pushout. Okay, and I might have said it before, but let's do it one more time. What's a pull? What's that? So a pushout okay, it's written sometimes like this: A disjoint union B, or A whatever. Okay, but keep in mind F and G. Okay, so it depends on F and G. So it's an object with maps going here and here. These are usually called projections, okay, or onto maps, okay, and such that it satisfies a universal property, namely, okay, I'm sorry, let's restate it. It's maps going like this such that this commutes, and it has the following universal property. I shouldn't call that D, C, because we have C, so let's call that D, okay. If there's any other object such that this map composed with this is equal to this composed with that, then there's a unique map like this such that this diagram commutes and this diagram commutes. Let's do it in terms of sets. Okay, if you have S, F, R, T, G, okay, then the push out of this is as follows. It's R disjoint union with T, this and this, subject to the following requirements. Okay, so this has the disjoint union of these guys and this guys, but we set certain things equal to each other. Namely, we have an equivalence relation, and the equivalence relation is generated by these little s's, and so we have g of s is equivalent to f of s. So take this thing, but certain elements in T will be crushed together, made in one, if they both come from the same f and g. Okay? Now, again, there could be more things that you can do that. You can crush more things. Universal property means exactly those things. It's these, the r's, disjoint union with t's, such that the t's are made to be crunched down to that. Okay, great. Let's see what else we have. Okay, great. So now we can recap. Okay, and we recap as follows. We're talking about limits and colimits. What are limits and colimits? They're diagrams. They're completions and co-completions of diagrams. Okay, so you have a diagram, and we looked at discrete diagrams. We looked at a diagram with one arrow. We looked at a diagram with two arrows. We looked at diagrams pointing this way. We looked at diagrams pointing that way. Pushouts, pullbacks. Okay, lots of diagrams. Well, any type of diagram can give you a limit and a colimit. Okay, and the way we do it is as follows. Just following the notation here. Okay. D is some diagram in a category, some part of a category. We're going to see later on how to do this more formally, exactly, better, okay? But that's in chapter 4, okay? And so what you have is the limit of D, and that's going to be an object in the category, and there's going to be a lot of morphisms from here to here. Instead of writing a lot of morphisms, we're going to just do one of those, okay? Okay, for some odd reason, this arrow goes like that. There's an arrow underneath it. It's called the limit. Okay? Okay. Now, this is to be thought of as the completion of this diagram. It's the object, such that the maps going down to it commutes with all the diagram, with all the triangles, etc., etc. Okay? But we can also do dually, we can do the colimit. Now you can write the colimit as colim or of D, or you can also write it as lim of D with a forward arrow. Okay, but and again, the names go back for different areas of math where they were generated. These are also called the direct limit, the inverse limit, the direct limit, inverse limit. Okay, we call it colimit, but it's also called the inverse limit, the direct limit. It has lots of different names because it has a rich history and it shows up all over in algebra and in topology, in everywhere. Okay, great. And those diagrams are what we have. Okay, now, some other ideas, okay? Okay, namely, limits and colimits, especially of finite diagrams, can be made from other smaller limits and colimits. Okay, so there's a lot of different theorems like this, and I don't want to go through all of them. I definitely don't want to prove them, but it goes as follows: finite limits. Okay, what does that mean? If the diagram is finite, it has a finite number of dots, it has a finite number of arrows, then you can take the limit of that, okay? And how do you take a limit? Well, we saw how to take a limit, but there's a way of getting the limits by just using products and equalizers. So if you by the way, products is a type of limit, equalizers is a type of limit. So if you just have finite products and finite equalizers, then you get all limits. So when you're checking to see if your category has all limits, all finite limits, instead of trying every single type of diagram, you have these building blocks of diagrams. These building blocks of diagrams if they have these building blocks of diagrams, then you get them all. Okay, so finite limits. Okay, they're equivalent to the fact that you have finite products and finite equalizers. Okay, but that's an amazing theorem, because what it says is any type of weird, strange diagram that you have, well, if you just have completions of these things, products, and completions of equalizers, if you have equalizers, then you have all of them. Okay, there's another similar thing. Okay, this also corresponds to, let's just make sure we have it right, pullbacks. All you have to have is pullbacks and terminal objects and a terminal object. Okay, and the way this is actually not hard to see. If you have a terminal object and a pullback, then you get products, and you can, if you have pullbacks are special types of equalizers. We can show how that works. Okay, so these two theorems show you easy ways to see whether or not you have finite limits. Great. What about colimits? Okay. Well, I don't even have to do that. You ready? Finite colimits is if you have finite coproducts and finite coequalizers. Okay, everything falls out of duality. So finite colimits comes from coproducts and coequalizers, or, okay, another way, that was pullbacks, this is pushouts. Okay, that's the dual of pullbacks and initial objects. Okay, so if you have these building blocks, then you get all finite colimits. So these are very helpful ways of checking whether or not you have limits or colimits. Okay, all this, limits and colimits, very nice stuff. We use it over and over and over. Okay, but we're going to revisit this in section 4.6. And we're going to see a nice clear way of describing all limits and colimits, a better way of doing it than what we have here. Okay? Main things you should get is that you should get these names of these limits and these special types of limits and colimits. Products, coproducts, equalizers, coequalizers, pullbacks, pushouts. Okay? These are all special types of things. Initial objects, terminal objects, they're also types of limits. Okay, and again, we'll see this all in section 4.6 again. Have a wonderful day.